The Technical University of Denmark runs the DTU Climate Change Technologies program. An essential part of the program includes an international workshop series where industry, science and public authorities have discussed and recommended fast-track avenues for development and deployment of new technologies. The results and recommendations from the workshops were presented at the DTU Climate Change Technologies Conference on the 17th of September 2009. The conference gathered key representatives from academia, industry and government who gave their viewpoints and recommendations on how to meet the climate change challenge. This DVD gives a summary of the conference and provides you with a comprehensive overview of the technological challenges and possibilities to develop the global society towards sustainability.
Good morning. My name is Lars Pallesen. I'm president of DTU, and it's indeed a great pleasure for me to welcome you to DTU Climate Change Technologies Conference. Climate change has become one of this decade's most important topics. It affects everybody, and everybody can and should contribute to solutions. Academia should not only predict the future climate and analyze consequences, but also point to solutions. In particularly, that holds true for technical universities. The climate change scenarios call for joint and dedicated effort to accelerate the use of existing and new technology, and in particular, it calls for new technologies that we can't even think of today. Solutions that can ensure the existing and the coming emission targets, and certainly also secure the well-being of mankind on this earth. DTU has launched the Climate Change Technologies program to ensure that DTU contributes significantly to the development and implementation of new solutions needed to solve the climate challenge. In line with our mission, DTU has thereby made a dedicated effort to gather the most relevant stakeholders to discuss and identify means and roadmaps for accelerating development and deployment of climate change technologies. This has taken place in 10 different workshops during the last year. In the results of these workshops that serve as reference point for this conference, we will present the recommendations and the conclusions.
DTU presented a conference paper that summarizes the conclusions and recommendations from the workshop series. It covers fields of technology related to mitigation, impact assessment and adaptation, and how to partner up in tackling the climate challenge.
We have three conclusions, three statements. First is concerning mitigation, that should be solved by developing a sustainable energy system. But that needs radical changes in the energy system, not only in the producing level, but also industry processes and end-user technology. Adaptation, we need a completely new approach to planning and management of key sectors in the public management. And then finally, to do this in 10 to 15 years, to revert the trend and afterwards half the emission, really is a challenge which needs that we do our best to enhance the innovative capacity of our societies. Now, first one, the sustainable energy system can be done, it can be done actually, by having three interdependent and simultaneous actions. First is to develop the intelligent energy system. That is required in order to boost or to take care of a massive amount of renewables, which each has a different energy profile, supply profile, and it also have variable supply profiles. The intelligence of the system is also necessary to harvest the massive potential of energy efficiency in transport and other end-use buildings and other end-use sectors. We need smart, say, end-user technology, and in order to harvest the potential, we need a system which interacts two-way with this. We have another section also concerning adaptation, where we need a new approach actually to how we manage and plan our society. We see three things to do. First is to embark on getting reliable climate predictions. They are fundamental, they are a need if we really want to get more sophisticated and useful planning tools. Next is climate impact, to study how would a changing climate itself and also the growing population of the world, because climate change is one thing, population growth from 6 million to 9 billion is another thing which needs to be taken into account. So how will climate changes and other demographic changes impact the natural carbon cycle of the Earth? And finally, develop some tools. We have a section in the report dealing with what can we do to make this happen, and happen fast. We give a number of recommendations, all devoted to be more efficient in our work. And our work, that is, of course, from a university point of view, but also from industry and public authorities. A key recommendation, actually, is that we need to be much more collaborative, but here we have some of them. First of all, that it's the same technology we're discussing all over the world. So global partnerships in aligning research strategies, national research strategies, is really something to opt for. Sharing large-scale facilities and share tasks in our technology innovation work. Partnerships between the three parties we have been mentioning here. Of course, we often say that public authorities should take some decisions and get things moving, but they'll ask us what kind of decision. So we really need to get a much more rapid flow of information between these three parties and simply to take informed decisions, not only in the public sector, but also, of course, at our level concerning collaboration with industry and our research priorities.
There was a general consensus on the issues addressed in the DTU report, such as the challenge of decoupling economic activity and greenhouse gas emissions, as well as the three important mitigation steps.
As I read this DTU report, there's a number of times the report talks about decoupling, and I think it's a very important issue. Then I think we have to take this very seriously. As a number of people pointed out, economic growth and energy consumption are interrelated. And the question we need to ask as we look at these coupled issues is whether or not they need to be coupled. So we need to decouple them, and there are a number of things we need to decouple: energy and environment, energy and water, economic growth and sustainability, and so on and so forth.
So what does it take to get to a sustainable energy supply and an integrated energy system? I think the three steps have been already partly discussed in the previous presentation. So energy mix, I think, is one important thing. Efficiency along the whole energy conversion chain, and at the end, smart grids, systematic optimization.
The development of a new intelligence energy system comprised a substantial part of the solution to reduce CO2 emissions. Several speakers outlined the importance and requirements of such smart grids.
If we look at today's energy system, we are up against a situation where this has been developed over the last, say, 100 years, primarily to provide electricity for the customers. And it has been developed in a way where we are utilizing central power stations and gradually introducing smaller wind turbines and other new technologies. However, if we are going to a future system where we have to rely on a large number of variable small energy sources, primarily renewables, we have to change the system completely. This is just an example of how the traditional energy system are looking. We come from central power stations to distributing electricity to the end users. What we expect is that in the new system we should make use of information technology, communication technology to a very large extent, and link this with the energy system, and then further on add it to the system also, let's say, the small local production units, the end users in the form of buildings, in the form of transport sector, and so forth. And if we combine these things all together, we get what we will call the future intelligent energy system.
So I think not everybody knows that fluctuating energy means to have a new grid, because the existing one is a dumb one. So and what we need is intelligence on top of the existing hardware to make it two-directional and to make it sensing and acting. And for that you need smart meters, you need grid intelligence, and on top of it you need to connect the whole thing to the IT of the utilities, that they can really bring what is expected behind it, that a better consumption behavior is really creating efficiency. And there are studies out in the world that if consumers know how much they consume in a given moment per day, and they change their behavior towards different consumption, so to speak, then there can be an efficiency improvement of 7%.
But of course, this doesn't work unless we can also deal with the pieces of the grid that will supply all this electricity to those of us who want to use it in a vehicle. You can imagine many more connections on the low voltage side of the grid. We now need to be able to deal with the intermittencies at all kinds of timescales, from millisecond timescales to day-night to winter-summer. We need to move power over bigger distances, and we need to use sensors and active controls. Right now in the United States, at least, we manage the grid by turning power plants on and off. We need to do better than that. The comment was already made that real-time measurement, communication, and control is an important part of this, and it needs to be robust and tolerant of failure. And this, at least in the United States, is going to require a totally different market from what we have now. So we have the option now, and I think we actually must in this century transform the world's energy systems. But this is surely one of the biggest challenges we have faced as a group of humans. But we have to do this in order to sustain the kinds of societies that we have built so far. Again, I would say no single solution. We need to work across a portfolio with a portfolio of timescales, research, and implementation. And then we really need to get to work on deep penetration of renewables from a variety of points of view, not just from transportation. Thank you very much.
An intelligent energy system is a prerequisite for increased use of sustainable and renewable energy sources. Conference speakers stressed that a new mix of sustainable energy technologies are required.
If you look at the future could be like that. So the next 32 years, if you are exploring continue the exploration of sugarcane, we have the contribution not only the rosy one, that is ethanol, but above the rosy one, you have all the contribution of electricity. We can generate a huge amount of electricity from the same feedstock. And then on top of that, the blue one, the bluish one, is carbon capture and storage. In reality, it's carbon storage, because this is carbon capture and storage from fermentation. And the yellow line that you see shows that if you are above that number, you are doing negative emission.
What we are hoping for, of course, is the government would use pretty simple objectives so that it's known what does the Danish government, for example, want to achieve with its climate policy. We'd hope that it's as much as possible technology neutral, what it implements. Of course, this cannot always be the case for timing reasons, for example, as I revert to in a little while. And then, of course, for us and other people, for us to invest in research, but much more importantly for our potential customers, to invest in facilities. They need to know that this is a long-term strategy by a government.
The message is, when you look into forecast 4, and we always use 2020 and 2030, and status, I think the message here is go to 2007, that column, and then compare 2007 and 2009, always to 2020 and 2030 numbers. You can see that there's a dramatic mix change. So, and that, in my point of view, is reflecting, first of all, the target setting, but secondly also that people have realized that we need into renewable energy, and you also can see that a significant portion of fossil energy still will be there in 2009.
The general conference opinion was that the use of fossil fuels is needed during the transition period to become a carbon-neutral society. Hence, the technology to capture and store CO2 needs to be further developed and deployed. This was addressed by several speakers.
The last part of my presentation deals with the carbon capture and storage part. Here, there's a real challenge in you have to deal with simultaneous development, both of capture processes, transport processes for CO2, and also the storage processes. Different kind of challenges, but they have to be met simultaneously. So you have to be sure that there is a market for the processes after the development. For the capture processes, there exist a lot of technologies under development now, the first generation amine processes, and there's a lot of other processes under development. One of the challenges with the amine processes is that they happen at very low temperature and are very expensive energy-wise. If you can move the capture process and the desorption process to a higher temperature level, you may have a much lower specific heat consumption, energy consumption.
Large-scale CCS demonstrations, to get from here to the commercial phase, you do need to have those demonstrations. The amount involved is greater than company balance sheets are likely to be able to justify, especially at a time of reduced liquidity. And only by doing the demonstrations are we going to make that final step from proven technology through to effective operation and unpack those issues around transport, storage, the business model, and so on.
Where policy did more than just say 20% targets, as with this technology thou shalt now produce electricity from coal differently. And that is, as John rightly pointed out, it's in the European Union, but it's also beyond this, that we should have demonstration plants. Now the European Union has decided, and that's very rare, that the Commission has gotten 5 billion euros, which is a lot of money for us, to do something about energy. There was budget available that hasn't been spent on agriculture, and then after some haggling, heads of states, all of them said, okay, you spent 1 billion on CCS demo plants. So this is just to say, that was, I think, quite courageous from all parts, because we see the technological challenges. We don't even know whether we can go into demo and certain of these issues.
There was general agreement that we need to develop all types of sustainable energy technologies. However, since they were competing for the same funding, the question on how to pick winners was addressed.
What is the right balance between taxing the bad and picking the winners?
Just to kind of reiterate, I think it's important to try to create a level playing ground. I also agree that when you are developing a completely new technology like carbon capture, for example, or like different types of biofuel, that since they are kind of so different from the existing infrastructure, that government have to step in and support some of them. I think it's important that they don't upfront pick the winner. In the US, for example, as I said, DOE has not said it has to be bioethanol. They've said it has to be from cellulosic raw material. And different types of technologies have actually been supported equally. It's just that, so far we are a little ahead in the game compared to the people that are doing gasification. For implementation, I think different technologies have to be kind of facilitated. Then, of course, the way to create a good market would be a high price on carbon. And then I think we would be fooling ourselves if we believe that the energy sector as we know it today is not subsidized in so many ways that none of us can really comprehend. Already as it is. So I think all of that has to be kind of shown in a clear picture, and then we have to take it from there, and the best man wins.
Massive energy efficiency measures are a prerequisite to meet the growing energy demand, and to develop a sustainable energy system. The potential, especially within the transport sector, was illustrated.
So, second step, efficiency, and here you can see again the setup of Siemens Energy. As I said, oil and gas, power generation, power transmission, power distribution, and I picked a couple of examples of existing technology and what is the efficiency improvement compared to state-of-the-art technology or recent technology, and I just want to pick one, which is efficiency up in the column, which is headed by power generation. So you can see that a combined cycle power plant, state-of-the-art existing technology has an efficiency level of 58%, and our technology is approaching 60 and more, and that is the product. It's called the H8000. It's a gas turbine which we have installed in Germany, which is already out of the test phase. So it's proven that we achieve 60% efficiency, and we are now going worldwide on sale with it. Just to give you an idea what the 2 percentage point efficiency increase really means, it's the CO2 emission of 20,000 cars, mid-sized cars, with a mileage of 10,000 kilometers per year. So that's significant.
As also already mentioned in the introduction, shipping is by far the most efficient mode of transportation we have today. It's maybe 60 times more efficient than air transport, 5 times more efficient than trucking, but even 2 to 3 times more efficient than rail transportation. So that by itself indicates that at least if we have the alternative, then transport by ship is far more efficient. That being said, there's no doubt that we in our industry and Maersk Line as well, we do consume and burn a lot of fuel. So it's a huge impact to the global environment. I think that the number is that 3 to 4% of the global fuel consumption is actually by shipping. So it's a huge contributor. It's not as huge as for instance, road transport or heating, but it's still very, very important. So obviously we do a lot to see how can we be more efficient in the way we actually use energy. And here is just illustrated 2 examples, a waste heat recovery system. Basically, how can we apply that technology on board our ships, basically getting a cylinder extra for our propulsion, but also a lot of research going to optimizing the hulls of the ships so we can reduce the energy that way. We have at present more than 100 specific projects focusing on how can we reduce our energy consumption.
So the car we have developed, we are still working on it, but we have demonstrated viability of the concept. We draw electric power from underground cable. So we embed the cable under the ground, about 4 or so centimeters below the surface, and then we send magnetic field, and we pick up the magnetic field, and we convert that into motive power, and then we run the motor. At the same time, we charge the battery if battery power is low. We also use the battery when you accelerate, so we don't have to depend wholly just on the... So this car has a small battery, and then this car can go from the house or wherever the person is staying using the battery power, because battery can take these cars maybe 30 kilometers. And then once they get on the road that has embedded electric power cable, then it draws the power from the ground, and then it doesn't use the battery power anymore. And so we demonstrated that indeed it works. We built a bus, we put the cable in on our campus, and then we have SUV built this way. And as we do more and more research, we are continuing to increase efficiency. It has been a lot of fun. And interestingly, most engineers think it's not going to work. It's an interesting phenomenon I found, why the technical people are most skeptical. We show them, but still they don't believe it.
I can't resist responding to this to the
get
challenge. The really big near-term target is energy efficiency. In the United States, we have left ourselves huge room to be more efficient. That's the politest way I can say it. And most of these will be at negative amortized costs. So there's a heck of a lot we can do on that shorter term time scale, even as we work on all the other technology options.
Time is of an essence in order to reduce CO2 emissions. An accelerated effort is required and can only be met by close collaboration between public authorities, industry, and the research society.
Now, what can really drive the R&D community at the world level? Well, that is when we're talking to the politicians, setting targets. Set ambitious targets, and don't be dissuaded if you find that there are some among us that say, oh, it's impossible to reach that. Well, set the target, and it might just be that we reach it, but more importantly, it drives research and innovation, and it drives competition, not only among companies, but among ideas. And most interestingly, perhaps, is it drives cooperation and alliances, because